Other substances with square root of 3 lattices abound, but the preceding examples suffice to show that the square root of 3 is an inseparable aspect of many common substances. The next logical question that begs to be answered is why this might be so. The apparent answer to this question is twofold. First, one must be familiar with what is commonly referred to as close packing. Close packing is a geometric exercise in which we observe the maximal number of similar spheres that can be packed into a given space. On the two-dimensional plane, a single sphere can be surrounded by 6 similar spheres, which effectively creates a hexagonal distribution. There is no other way possible to close pack more or less than 6 spheres around a single sphere, if all of the spheres are geometrically similar. In 3 dimensions, however, 2 possible close pack configurations are possible. If we build on the hexagonal pattern that we have just created, we can add first a layer of 3 spheres, and then another layer of 6 more spheres. The resulting arrangement is a close packed group of 17 spheres, and it coincides perfectly with the atomic arrangement that we saw earlier in metallic crystals such as magnesium and beryllium. In the second possible arrangement of close packed spheres, we begin with a layer of 5 spheres. Atop this, we add a layer of 4 spheres, and then a third layer of 5 spheres, similar to the first. The resulting arrangement corresponds exactly to the face-centered cubic structures that we have witnessed in several atomic lattices, including aluminum, sodium chloride, and diamond. The third type of common atomic lattice mentioned earlier was called bodied-centered cubic. If we interpret this arrangement as a close-packed pattern, we find that it comes extremely close to fulfilling the requirements to be considered close-packed. That is, although the body-centered cubic lattice is not a perfect close-pack arrangement, it is a very tightly packed formation. Considering the prevalence of face-centered cubic, bodied-centered cubic, and hexagonal close-packed molecular structures, it is safe to say that close packing is a common aspect of molecular formation. Although we can't say that close packing is the cause of how molecules form, it would seem that nature tends to fill space with atoms in the most compact and efficient means possible. To answer why matter would tend to organize itself in close-packed patterns, we must turn to the work of Sir William Rowan Hamilton, an alcoholic Irishman who lived in the early 1800s. Sir Hamilton was a child prodigy and mathematical genius, and his work is credited with laying the foundation for the modern physical study known as quantum mechanics. Amongst other mathematical discoveries, he discovered what has been labeled the principle of least action, which states that a given substance will structure its molecules in such a manner that the lowest possible potential energy is achieved when its formation is complete. To effect the state of lowest potential, an atom must structure itself in such a manner that it is able to resist external stress readily. In order for a material to share stress across its entire structure, the arrangement of that material's atoms must have elements that are equally spaced from one another. By forming in regular geometric polygons, every point in a given structure flexes to resist force applied to any point in that structure. The triangle pictured here is physically the strongest form possible in 2 dimensions, not only because all of the points in the structure will share external stresses equally, but also because it has the fewest number of points required to create a regular polygon. The fewer the number of equally spaced points that are found in a lattice, the stronger that lattice will be. Because close-packed structures meet these requirements better than any other form, we find that nature chooses to employ them over and over again. Thus, we begin to get a glimpse of the great logic that lies behind the prevalence of the square root of 3 and its related geometric forms in the foundation of the matter in this universe. But where does this leave us? What can we do with this information? We can employ it in our art and architecture, as have so many cultures before us. We can use it scientifically to understand more about the physical forces that shape this universe, as have the physicists since time immemorial. And perhaps, most importantly, we can teach it to our children, so that they too may understand that we do not live in a cold mechanistic cosmos, but that we live in an indescribably complex world that is based on a few beautifully simple principles. It is this sense of awe and respect for that which surrounds us and gave birth to us that is sacred geometry's greatest gift.